6 comets, plus the interstellar visitor 3, I/Atlas, are all closing in on the Sun within 30 days of October 2025. Astronomers expect maybe 2 or 3 bright comets a year, but this time the lineup is 7, all at once, including a visitor from another star system on a hyperbolic path. Is it a cosmic coincidence, a natural clustering never seen in modern records, or does the data hint at something more? The odds, the origins, and the world's only past 3 I/Atlas set the stage for a discovery that could rewrite what we know about randomness in the solar system. So what's actually driving this wave? An unseen hand, or the wildest celestial jackpot in living memory? When a comet plunges toward the Sun, a quiet transformation begins. At first, it is nothing more than a frozen speck, ice and dust locked together, orbiting in deep cold. But as the comet draws closer, sunlight grows fierce. This is perihelion, the moment of closest approach, when the Sun's heat is most intense and the comet's true nature is revealed. At perihelion, a comet's surface can warm by hundreds of degrees in a matter of days. Ice is buried beneath the crust, water, carbon dioxide, ammonia turn directly to gas. Pressure builds, cracks open, and jets erupt from the nucleus, firing streams of vapor and dust into space. These jets do not just sculpt the comet's appearance, they can nudge its path ever so slightly, tweaking the orbit by fractions of a second. For most comets, these changes are minute, but they are a signature of just how dynamic these objects become as they race past the Sun. The result is a coma, a glowing envelope of gas and dust that can swell to tens of thousands of kilometers across. Sunlight scatters off this cloud, making the comet visible even from Earth. The coma is the source of the comet's brightness, measured in magnitude. Astronomers use this scale to track how easily a comet can be seen. Lower numbers mean brighter objects. For a comet to be visible to the naked eye, it needs to reach about magnitude 6 or less. Many never get that bright, fading in the background or lost in the Sun's glare. But when conditions are right, a comet can outshine the stars, dominating the night sky with a ghostly glow. Then there are the tails, 2 distinct kinds, each shaped by different forces. The dust tail, broad and curved, forms as sunlight pushes tiny grains away from the coma. It reflects yellow-white light, arcing gently along the comet's path. The ion tail is a sharper, bluer streak, carried straight back by the solar wind. This stream of charged particles sweeps molecules away at high speed, sometimes causing the tail to snap or disconnect entirely during solar storms. Both tails point away from the Sun, but their angles and colors reveal what is happening at the heart of the comet. Every approach is a race between heat and time. Some comets flare up, then fragment or fade before they are ever seen from Earth. Others survive the encounter, looping back into the dark for another orbit, sometimes centuries later. But for the brief window around perihelion, every comet becomes a laboratory, its brightness and tails recording the invisible dance between ice, rock, and sunlight. The language of magnitude, the drama of jets and tails, these are the clues astronomers use to predict which comets will become legends and which will vanish without a trace. On Mauna Loa's dark slopes, ATLAS, short for Asteroid Terrestrial Impact Last Alert System, keeps watch for intruders. In May 2025, it flagged C/2025 K1, a comet brightening fast, with perihelion set for October 8th. Early projections showed a risky solar pass, a possible breakup, and a magnitude just above 5.2, enough for binoculars. Atlas's alert was only the beginning. In September, the SWAN instrument aboard SOHO caught C/2025 R2. SWAN specializes in ultraviolet, spotting comets by their hydrogen emissions. This one promised a close approach, 0.27 astronomical units from Earth, peaking around October 21st. Its southern trajectory and forecast magnitude of 4 raised hopes for a naked eye show if its activity held. Stereo, usually tracking solar storms, found 414P, a faint, fast sungrazer. These comets skim the Sun, risking disintegration before swinging away, each comet distinct, but all converging on the same days. The Mount Lemmon survey above Tucson contributed C/2025 A6, or Lemmon, a periodic visitor with a mapped orbit. Lemon's perihelion also falls on October 21st, overlapping with Swan. Its brightness is unpredictable. Some models suggest magnitude 3, others as faint as 8. Lemon's northern path means observers from Europe to Canada will have a clear view. Pan-STARRS, another Hawaiian survey, added C/2025 K1. This newcomer isn't expected to dazzle, but its timing matters for the cluster. Each comet comes from a different search: robots, solar instruments, ground-based surveys. Their orbits cross and diverge, yet the calendar keeps drawing them together. Above them all is 3I/Atlas, the interstellar outlier, spotted by Atlas in July 2025. Its hyperbolic path and outbound-only trajectory mark it as the third confirmed visitor from beyond our solar system. Its perihelion falls on October 29th, just after the main group. Its arrival during this crowded window turns a rare event into something astronomers struggle to quantify. For the first time, 7 named comets, each tracked by a different instrument, will peak within days of each other. The Discovery network stretches from ground to orbit, ultraviolet to visible, weaving a global web of vigilance. With every new detection, October 2025 grows more crowded, setting the stage for a clustering that resists easy explanation. In a typical year, the sky offers up its cometary wonders sparingly. The historical record, stretching back through a century of careful observation, shows a familiar rhythm. 2, maybe 3 comets bright enough for binoculars, each spaced out across the seasons. Most years pass without any naked eye spectacle at all. When a comet does flare into view, it's usually a solitary performer, not part of a crowd. Astronomers, both amateur and professional, have grown used to this measured pace. A slow drip of icy visitors, each arrival a minor event in the quiet ledger of the night sky. Catalogues from the Minor Planet Center and the International Astronomical Union bear this out. Between 1900 and 2022, the mean number of comets reaching binocular visibility per year hovers just above 2. Some decades, like the 1950s or early 2000s, see brief upswings as new surveys come online or as solar activity stirs up more distant objects. Yet even with the advent of all-sky search programs, NEAT, Pan-STARRS, Atlas, the basic cadence holds. Bright comets remain rare. Their arrivals are scattered, sometimes separated by months or even years. The records show only a handful of cases where 2 comets reach similar brightness within a few weeks of each other, and those episodes are the stuff of stargazer legend. The clustering forecast for October 2025 stands out against this backdrop like a lightning bolt on a clear night. Instead of 2 or 3, the calendar shows 7 comets peaking in less than 30 days, including an interstellar interloper. The numbers strain belief. Monte Carlo simulations, using a century's worth of perihelion dates and brightness estimates, suggest that the odds of 6 bright comets and an interstellar object all crowding into a single month are less than 1 in 30,000, possibly as rare as 1 in 100,000. Even after correcting for the improved sensitivity of modern surveys, and for the fact that today's telescopes catch fainter, more distant objects than ever before, the probability barely budges. The clustering is not a trick of technology. It is, by every statistical yardstick, an outlier. Astronomical communities notice the anomaly almost in real time. In early 2025, as ephemerides for newly discovered comets were posted to open sky forums, a pattern began to emerge. Visualization tools, once the province of professionals, let hobbyists overlay orbits and spot the swarm for themselves. The sense of surprise was palpable. No one could point to a historical precedent. The archives simply didn't contain it. Survey bias, the perennial suspect in any explosion of new discoveries, fails to explain the timing. While more comets are found now than in the age of photographic plates, the true rate of arrivals, especially for the brightest, most visible objects, has not changed enough to create this kind of pileup. Solar activity, peaking in 2025, does boost the number of sun grazers and can shake loose a few extra fragments, but it cannot manufacture a parade of major comets, each on its own distinct path, converging on the same month. The clustering is not just a quirk of how we look, it's a real, physical event written across the sky. Statistical outliers invite speculation, but they also demand rigor. The 2025 swarm is a natural experiment, a stress test for every model of cometary arrival and detection. In the coming months, astronomers will comb the data for hidden connections, shared origins, orbital echoes, hints of fragmentation in the distant past. But for now, the numbers speak for themselves. October 2025 will be a month unlike any other in the history of comet watching. A statistical spike that resists easy explanation and sets the stage for a deeper search for causes. Statisticians at the International Astronomical Union ran the numbers as soon as the October 2025 lineup became clear. They turned to Monte Carlo simulations, a digital lottery drawing random comet arrival dates from over a century of observations. Each run asked the same question: how often do 6 bright comets, plus an interstellar visitor, all peak within a single month? The answer: almost never. In 1 million simulated years, the clustering appeared just a handful of times. The raw odds, less than 1 in 30,000, are so remote they leave most probability charts gasping for breath. Survey bias is the first suspect in any statistical surprise. Modern sky surveys like ATLAS, Pan-STARRS, and SWAN sweep the heavens with relentless efficiency, catching faint comets that would have slipped past earlier generations. But even after adjusting for these sharper eyes, the anomaly barely softens. The simulations account for every gain in sensitivity, every uptick in discovery rate since the year 2000. The result? The chance of this many bright, distinct comets crowding into a single month drops even further, to less than 1 in 100,000. These are odds you would expect from a lottery, not the sky. Brightness, too, refuses to play along with simple explanations. Survey telescopes find more faint comets, but the number of truly bright, naked-eye candidates has remained stubbornly steady for decades. The 2025 cluster is not a parade of marginal objects boosted by better cameras. It is a convergence of comets that would have stood out in any era, each one crossing the visibility threshold by its own merits. The historical record, spanning photographic plates, logbooks, and digital catalogs, shows only solitary flares and the rare double act, never a gathering like this. Visualizations from the Minor Planet Center lay out the past century in stark relief. Most years, the calendar is a sparse grid, with comet peaks scattered months apart. The few times 2 comets have approached perihelion together, astronomers took note. 3 in a month is a legend. 7, including an interstellar outlier, is a statistical spike so sharp it stands alone. No burst of solar activity, no uptick in survey coverage can conjure this pattern from chance alone. The numbers, once stacked, refuse to be ignored. Probability models, detection corrections, and brightness thresholds all point to the same conclusion. The October to December 2025 clustering is not a mirage created by human technology or statistical fluke. It is, by every measure, a physical event that strains the boundaries of randomness. The models leave one question hanging in the air. If chance cannot explain the swarm, what can? Suppose, for a moment, that these 7 comets are not simply obeying the laws of chance. What would it take to coordinate their arrival? Dr. Kevin Blanchard, part of the ATLAS discovery team, lays out the raw numbers. To herd even 2 comets onto synchronized paths, let alone 7, would require forces far beyond anything produced by natural jets. Typical non-gravitational nudges, measured by Marsden's A1, A2, and A3 parameters, barely register above 1/10 millionth of a g. Natural outgassing can shift a comet's speed by less than a meter per second over months. But to compress perihelion windows by days, the required delta V jumps to tens of meters per second. That's 100 times greater than the wildest comet outburst ever recorded. Artificial shepherding would leave fingerprints. Simultaneous outbursts, all outside solar storm windows. Chemical signatures, engineered isotopes, metals, or molecules never seen in natural comets, etched into their spectra. Synchronized orbital changes, visible as abrupt, shared deviations in the post-perihelion solutions. A smoking gun would be an isotope ratio so unnatural it could only be manufactured, or a non-gravitational acceleration out of family with every known comet. So far, the data is stubbornly ordinary. The Marsden parameters for each 2025 comet fall inside the expected range for their size and distance from the Sun. Spectral scans from ground and space show only the familiar fingerprints of water, ice, dust, and simple molecules. No engineered isotopes, no coordinated outbursts, no signals. The numbers leave little room for fantasy. If a hidden hand is at work, it hides better than any technology known to science. SETI's latest round of radio sweeps has come and gone without a single artificial signal. The Allen Telescope Array and Breakthrough Listen teams tracked every major object in the October cluster, focusing especially on 3I/Atlas during its closest approach. Across the spectrum, 1 to 11 GHz, hours of integration, no narrowband beacons, no engineered pulses, nothing but the hiss of natural emissions and the usual background. The silence is as telling as any positive result. If there's a message, it's hidden deeper than our instruments can reach, or it simply isn't there. Meanwhile, solar maximum has reached its peak. Space weather models show a sun bristling with energy, coronal mass ejections, high-velocity solar wind, and magnetic storms that rattle satellites and stretch comet tails to breaking. Every tail disconnection in the October swarm, every sudden brightening or jet, has coincided with a spike in solar activity. The timeline is tight. Lemon's brief outburst tracked a geomagnetic surge measured at Earth. These are classic signatures of solar-driven drama, not coordinated signals. No comet in the cluster approaches Earth closer than 0.27 astronomical units. Impact risk is 0. The real-world hazard comes not from icy visitors, but from the Sun itself. Solar storms that can trip power grids and jam spacecraft. As the watchlist grows, astronomers are lining up coordinated campaigns, spectral scans, astrometric tracking, and open dashboards logging every anomaly. The rule remains: extraordinary claims demand extraordinary evidence. For now, the data hold steady. No artificial accelerations, no engineered molecules, no synchronized maneuvers. The sky is crowded, but the verdict is clear. The test continues. What would change this picture? A signal, a non-natural isotope, a maneuver no comet could perform. Until then, skepticism is not just caution, it's the best tool we have. Still, the reasons behind such precise timing remain unsolved, as no known mechanism forces unrelated comets to converge in this way. As new observations come in during solar maximum, scientists will watch for any unexpected changes in spectra, motion, or fragmentation. For now, the 2025 comet cluster stands as a reminder. Our solar system can still surprise us, and every answer sparks new questions.